everybody. Welcome to the second lecture of my course on mathematical aspect of quantum mechanics. The goal of the lecture today is to give you a background on operator theory on Hilbert spaces, and we will see different kind of operators, bounded, closed, self-adjoint, and so on. The course might be a little bit abstract, but there will be many examples that will help you to grasp the notion that we will cover. So let's start with a very first notion, the notion of operator between Hilbert spaces. Actually, we have encountered already operator, but I want to make precise this notion here. So we're going to call an operator between two Hilbert spaces H1 and H2, a map which is not necessarily defined on the whole of H1, so it's only defined on a subset of H1 with two requirements. We require that dt is actually a linear subspace of H1, and the map T is a linear map in the usual sense on dt. So that will be our notion of operator. Of course, they are linear. Sometimes it's called linear operator, but since all the operators we're going to meet in this lecture are linear, I will just use the term operator. dt is called the domain of the operator T. And what is important to notice is that when you speak about operator, it's not just the action on the vectors, but it's also the domain on which it's defined. This will be crucial for the rest of the lecture. In particular, when both Hilbert spaces are the same, so when they are equal to H, we simply say that we have an operator on H with some domain dt. Particular case is the case of linear form. So linear form also might be defined only on a subspace of H, and since they are linear form, they take value in the Hilbert space C, which is one-dimensional. When H1 is infinite dimensional, one usually requires that the operator we consider are densely defined, but that's not always the case. And this means simply that the domain of the operator dt is a dense subset of H1, namely that its closure as a set is equal to H1. Also, I want to stress the fact that equality between operators does not only mean that the action is the same. I mean, the action on vectors is the same, but the domain also must be equal. Okay, so this is what we mean by this equality here. And in fact, this brings us to the question of extension. So let's say we have an operator T between two Hilbert spaces. We will say that an operator S between the same Hilbert spaces is an extension of T if its domain contains dt. Right? And we require then that on this domain dt, these two operators coincide. So another way to say it is that the restriction of S to dt is equal to T. And there is a useful convention for extension is this one. So this means that S is an extension of T. So it's very intuitive because it refers to the inclusion of the domains. Let's look at a very simple example of extension. So consider two operators T and S defined on the Hilbert space L2 of R, the space of square integrable function. And the operator T has domain dt, which is the space of continuous function with compact support. So of course it's a subset of L2 of R. It's even dense in L2 of R. And its action on the function is simply given by multiplication by x. So this is a very simple example of what is called a multiplication operator. And of course it's well defined, because if u is continuous with compact support, xux is also a continuous function with compact support, and therefore it's in L2. For the operator S, you consider, well, the action is the same as you could see here, but the domain is different. So we're going to consider the u, the function u, such that xux is a L2 function. So u doesn't even have to be continuous here, right? As long as xux is in L2, that's fine. And clearly, if u is continuous of compact support, then xux is still continuous with compact support, and therefore it belongs also to the domain of S. So this means that S is an extension of T. So this is a very simple example. Next notion is the notion of bounded operator. You probably have seen this notion before, so let's quickly review it. Well, it's an operator between H1 and H2. And we will say that it's bounded if there is a positive constant C such that this inequality is satisfied. Okay. And the 2 here refers to the norm in H2, and of course the norm in H1. Yeah. So C is not unique. If you have a C, then 2C is also possible. But the best constant, namely the smallest possible C, defines a norm. So it defines the norm of the operator, and it's simply given by the following expression. So you make this quotient for u different from 0, and you take the supremum on non-zero u in dt. Okay. I should mention that bounded doesn't mean that the map is bounded, because it's a linear map, and it simply means that when you restrict the t on the unit sphere, so the set of unit vectors, then it becomes a bounded map. In fact, bounded is synonymous to continuity in the case of linear operator, and in fact it's a little bit more than that. It's a bounded operator is also uniformly continuous, because if you consider the difference, let's say tu1, tu2, where u1, u2 are in H1, and you take the norm, so by linearity you have that, and since it's bounded, you have this inequality. So this means that T is uniformly continuous. In fact, boundedness is equivalent not only to continuity, but just to continuity at one point. For example, continuity at origin. This is a simple consequence of linearity of T. Now, let's look at 2 examples. A first example, well, it's an operator T, which is defined on the Hilbert space L2 of the interval 0a, and it's a multiplication operator by a continuous function f on the interval 0a. So you know that in that case, for a continuous function defined on a compact interval, you have a bound, right? This is valid for any x in the interval. So in order to show that it's bounded, you just basically have to use this. So you write down the norm square of tu, which is equal to this integral. Here you bound this term by m square, and then you're left with the norm square of u. And this shows that t is bounded. The second example is also a multiplication operator, but this time on the Hilbert space little L2n. And so it's defined on this domain, which consists of sequences in L2 such that this sum is finite. So this sum is nothing else than the norm square of NC, right? And to see that it's not bounded, well, it's sufficient to just notice a very simple fact that EK here denotes the element of the canonical basis of L2. They are eigenvectors of the operator n, so the eigenvalue is k. You form this quotient, and it's equal to k. So this shows that it cannot be bounded, because if it were bounded, this quotient would be bounded by some constant independent of k, but this is impossible. Let me make a few remarks on bounded operators. Well, first, as I said, the norm of the operator is the best constant such that this inequality is satisfied. So this is one thing. And second remark is that in the case you have a densely defined bounded operator, then you can in fact extend it uniquely to the full space. Okay, I will call the extension T tilde, and T has the same norm as its extension. So for bounded operator defined on a densely defined domain, practically you can consider that it's defined on the full space. So why is this so? There are two reasons. One reason is that, as mentioned before, a bounded operator is also uniformly continuous. So it will send Cauchy sequences in H1 to Cauchy sequences in H2. And also, H2 is a Hilbert space, so it's complete. And that's the only thing you need to show that. And in the case you have two bounded operators defined on the whole of H, well, by applying this inequality twice, one time for T and one time for S, you deduce very easily this inequality. So the norm of the product is smaller than the product of the norms. And last thing about bounded operators, well, it's more precisely it's a theorem on bounded linear form. It applies also for densely defined bounded linear form. It's Ries's theorem, which says that if you have a densely defined bounded linear form on H, then there exists a unique vector VL such that you can express the form by an inner product. So the value of the form L on U, so this is a complex number, is just the scalar product of VL with U. Right. And the norm of this linear form is simply the norm of the vector VL. This theorem, in fact, means that for those of you who heard about the Dirac notation of bracket, the Dirac bracket notation, well, you just write the scalar product, not that way, but you put a bar here, and you split it in two parts. So this is called a bra, and this is a ket. Ket or just vector in the Hilbert space. And you can see the bra as bounded linear form via the Ries's theorem. So this is the justification of Dirac notation, and somehow it's just to say that the linear forms and bounded linear forms and vectors in the in a Hilbert space or on the same footing. You have an isometry between them. This ends what I wanted to say about bounded operators. So the bounded operators are very nice, it's very easy to work with, but there is a fact of life that says that most interesting operators in quantum mechanics and even elsewhere are not bounded operators. Okay. So it's very difficult to work with bounded operators in general without further condition. In fact, there's no good theory. And one would restrict himself on a class which is in between bounded and unbounded operators. And this class is the class of closed operators that we're going to define now. You consider an operator between two Hilbert spaces, and you would say that it's closed if its graph is a closed set in H1 times H2. So the graph is simply the set of pairs U, T, U, when U is in the domain of T. So it defines a subset of this Cartesian product, right? And you can put a norm on this one, so you have a topology, so you can speak about a closed set. Just to give you an idea here briefly before we go into the details, if you have a bounded operator which is defined on the whole of H1, then it's a closed operator. So the class of closed operator includes the class of bounded operators defined on the whole of H. A kind of converse is that if T is closed and the domain is closed as a set, so this is important, then T is bounded. So this is a consequence of a theorem that you might have seen in functional analysis, which is called the closed graph theorem. It says basically that a linear map between Banach spaces or Hilbert spaces is bounded if and only if it's closed. Yeah. But here we have to be careful because our domain are not necessarily closed. In fact, in the most interesting cases, it's never closed. It would be a dense linear subspace of some Hilbert space. How to characterize closed operators? Well, it's very easy. It's exactly the same characterization as a closed set in a metric space. So you have a sequential characterization of a closed set. And saying that an operator is closed is completely equivalent to the fact that, to this property here, that namely if you take a sequence in the graph of T, so it means that Vn here actually is the image of Un by the map T, which converge to some element uv in H1 cross H2, then U must be in the domain of T and V must be the image of U. That's it. Or another way to say it is that the pair here, the limit, should be in the graph. So this is just the sequential characterization of a closed set. And there are a few consequences. I mean, using this characterization, you can easily show two properties that you will do in the problem set. That for a densely defined bounded operator, well, it's closed if and only if its domain is the whole of H1. So it's completely equivalent in that case. You probably know that the kernel, or maybe some of you call it the null space, namely the kernel of T is simply the element in the domain of T such that Tu is equal to 0. In the case where T is bounded, you probably know that its kernel is a closed linear subspace, right? It's just a consequence of continuity, because you just take the pre-image of 0, the set with one element which is closed, and so it's a closed set. For closed operator, you cannot do that. You need another argument. But you can still show that the kernel of a closed operator is also a closed linear subspace of H1. Okay, so you'll do that in the exercise sheet. Another notion, the notion of closable operator. Why we speak about closable operators? Because it's for a practical reason. It's usually difficult to define the domain of when it's possible, the domain of an operator directly so that it's closed on this domain. It's much easier to define a domain where the operator is closable, if it's possible. Closable means simply that an operator has a closed extension. So it's simply that. And this is usually, from the practical point of view, it's much easier to do. And so if it has a closed extension, you see that if you have two such extensions, somehow by taking the intersection of these extensions, you still get a closed extension. So you can speak about the smallest closed extension of this operator. Right. And if T is closable, so we know that there exists closed extension, the smallest closed extension is called the closure of T, right? And it's denoted that way. So that's an extension of T. Yeah. And it's not difficult to see that this is the same thing as saying that T is closable if and only if you consider the graph of T, you take its closure in H1 cross H2, and it's still the graph of some operator. So precisely the closure of T. So in fact, you can, in the case where T is closable, you can take this relation as the definition of the closure of T. Okay. So you should notice that in general, if I give you an operator T, I have its graph, of course. I take the closure of its graph, but there's no guarantee that this closure will be the graph of an operator. When it is the graph of an operator, then you say that this graph is closable, and this defines the closure of T. There is a similar characterization of closable operator. So namely, it's completely equivalent to this property. So if a sequence in TU converges to 0, and you need one more condition, that the image, so the TUN converges to in H2 to some element V, then this V must be equal to 0. So this is completely equivalent to say that T is closable. For example, let's consider this case. Again, the multiplication operator, and define on a continuous function with compact support in L2 of R, right? And then it's not difficult to show that T is closable. So basically, you should use Lebesgue theorem. So it's essentially an exercise in integration theory. And then you can find the closure of it. So its domain would be a maximal domain in a sense for this kind of operator. So that's all the U such that FU is in L2, right? Now, an example of non-closable operator. So we will work here in the case of H is little L2 of n, and En is the standard basis. And I will introduce one element here, U, which is defined in the following way. So that's the sum over n of 1 over 1 plus n en. It's clearly in L2 because the sum over n of 1 over 1 plus n squared is convergent. Its sum is pi squared over 6. So this is an element of L2. The specific form of this term is not so important. What is important is that you have infinitely many non-trivial terms in this sum. That's what is what matters. And I will denote, well, I will define first the domain of the operator by taking the linear span of the en and u. So we consider all finite linear combination of the basis element and u. Right. So the en, it's a Hilbert space basis, so it's they are orthonormal, they are linearly independent, and clearly you cannot write u as a finite linear combination of the en, right? The sum here is infinite, so you have a set which is linearly independent, and this means that any element in D, well, can be written in a unique way, okay, as a linear combination of u and the ek, right? So the finite sum, where the alphas are complex numbers. And since this expression is unique, okay, this definition of the action of T on V, which is, so on such a V, you would say that T on V is equal to alpha u. So you discard these one. So T, the way it's defined, is such that T on Ek is equal to 0. Okay. And as I said, this is well defined because this expression is unique. Then we will apply the previous criterion on closability. You consider the following sequence. Okay, you take u and you remove this finite sum, which are just the first terms, right, in the series that defines u. And of course, as n goes to infinity, okay, this is a vector in dt, it goes to 0. Also, by definition of t, so this is the operator t here, and T of un, well, this is a finite linear combination of Ek. I discard them, so I'm just left with u. So T on un is equal to u for any n. So it's a constant sequence, so it trivially converges. It converges to u, of course, but u is not equal to 0. Right, so this operator cannot be closed. Now I want to define a very important concept. That's the notion of the adjoint of an operator. It will be crucial for our discussion in lecture 3. So it is basically the generalization to our setting of the adjoint of a matrix that you know from linear algebra. Recall that the adjoint of a matrix in the complex case is the complex conjugate of the transpose matrix, right? Here, there is a little difficulty related to the fact that our operators are not defined on the full space, but still, it's not so difficult concept. So the goal is to associate to a densely defined operator on H, an operator T star, which has the adjoint property. Okay, so we require this relation to hold for any u in the domain of T and any v in the domain of T star. And for bounded operator defined on the whole of the Hilbert space, it's pretty easy. You don't have problem with the domains, and it's a direct application of Ries's theorem we have seen before. Actually, Ries's theorem will play a role here. So let's go through the details. Well, we consider here a densely defined operator on a Hilbert space. This condition is very important here. And we will first define the domain of the adjoint, dt star. So it consists of all vectors in the Hilbert space H such that the following, so this is a map from dt, u is in dt, and it takes value in C, it's a linear form. We require that this linear form is a bounded linear form on dt. So we look for all the v such that this linear form is bounded. Well, clearly this set cannot be empty because v equals 0 give us the zero form, and the zero form is obviously bounded. And it's easy to see that it is also a linear subspace of H. So we define this linear space in the following way. Then, well, this is a bounded linear form on a dense domain. So we know that by Ries theorem, we know that there exists a unique vector that I call V star, such that the value of the linear form on U is given by a scalar product, right? And since V star is unique, well, we define a map which associates V stars to V, right? And I think it's easy to see that V star depends linearly on V. So we have defined an operator on this domain. So the adjoint is, well, you have the formal definition here. It's the adjoint of T is an operator which is uniquely defined by the condition that we have studied before. So the domain is the set of V such that there exists a unique V star such that this relation holds on dt. And then you define a T star on V by associating V star to the vector V. So this is the definition of the adjoint. For example, let's consider two cases. Again, a multiplication operator on L2 of R by a continuous function. Well, continuous is not essential here. It can be any measurable function, but doesn't change anything. So T acts by multiplication by F. We take as domain, which is an obvious one, is the space of continuous function with compact support. And so this is dense in L2, so we have a densely defined operator, so we can speak about its adjoint. And its adjoint is simply the multiplication operator by the complex conjugate of F. Yeah, this is very easy to see. And the domain of this operator is just the set of U such that Fu, the product, is in L2. It's nothing more. In fact, we can be a little bit more explicit. So you see that if I write this condition, the condition that appears in the domain of T star, so I'm looking for all the V such that I can write this inner product in the following way, right? But Tu is simply multiplication by F. So this is VFU. And then I can pass F on the other side, but I need to put a complex conjugate. So I have this. This is equal. But you see here, this is the scalar product for the Hilbert space structure. So this element here, f complex conjugate v, should be in L2, right? And so I should put this condition, and it's precisely this one here. And so if v is in the domain of the adjoint, then this is in L2. This is fine. Then I have equality between this and this, and you see that u, well, the domain of T is dense, right? So I must have equality between V star and F complex conjugate times V. So this defines the action of T star. The second example is on the momentum operator that we've met already, and we consider this operator, so it's a one-dimensional, so its domain would be the space of smooth function with compact support, so it's dense in L2, so we have a densely defined operator, and we will see that it's the domain of its adjoint is the set of function in L2 such that its derivative is in L2. But I will put quotes here because it's not the derivative in the usual sense. I will explain it. And the action of P star is simply well, the same action as P. Yeah. Okay, what about the codes? Yeah, you see here it's not the usual derivative. I'm not assuming here that U is of class C1 or Q is differentiable. So I'm not saying that the domain of the adjoint is the set of differentiable function whose derivative is in L2. Right? It's a little bit larger than that. So this derivative is what is called a weak derivative, and it is essentially defined by the integration by part formula. So namely, if I write the integration by part formula, so this is the inner product in L2, so that's an integral. And you have boundary terms. Okay. Well, U is C infinity with compact support. So you won't have any boundary terms. Okay. And so this makes sense. So this gives me a smooth function with compact support, and I take the scalar product with V. But now I want to know the condition on V such that I'm able to express this scalar product as a second scalar product, namely this one, with some function that I write in that way. So this is possible if V satisfies certain property. In fact, V must be what we call an absolutely continuous function. So namely, a continuous function whose derivative exists almost everywhere. Okay, and of course it should be in L2. Yeah, and you can show that in that case, well, this function here is uniquely defined because of the density of C infinity. The set of function, smooth function with compact support is dense in L2, and we call it the weak derivative. So the integration by part formula works perfectly well here. So this defines the domain of our operator, because if you write it in terms of P, well, you see here I have a minus sign, but in P I have the complex I, so this is exactly this relation. Okay. So namely, this is P on U, it's equal to, well, this would be my P star on V, right? So we get exactly, as mentioned here, the same action. And this space has a name. It's called, it's one example of what is called a Sobolev space. If you do some PDE, you will meet them. Yeah. So this is another example of computation of the adjoint. Now I want to introduce two more notions. They are closely related, but we should be careful and distinguish these two notions. The first one is what is important for us is the notion of self-adjoint operator. Of course, in lecture 1, I used the term self-adjoint without being very precise about it, but now we will define it precisely. Well, we have everything to define it. And, well, it's a densely defined operator on a Hilbert space such that it's adjoint. So we know that we can speak about its adjoint because it's densely defined. So its adjoint is equal to the operator itself. So this is a self-adjoint operator. And by definition of the adjoint, it satisfies this relation. So this is valid for any UV in the dt or d t star, right? This is the adjoint relation. Another notion, which, well, you don't need that the operator is densely defined for that one, because the definition doesn't refer to the adjoint, is the notion of symmetric operator. And so it's any operator which satisfies this condition here. So we have a similar kind of condition, but we require it to be valid for UV in the domain of T. So this is symmetric. It should be clear that a self-adjoint operator is also symmetric. Yeah. The converse is not true. Even if the symmetric operator is defined on a densely defined domain, it's not true that it is, in general, self-adjoint. And a word of caution here, if you, let's say you want to learn some more quantum mechanics and you look in a physics book, these two notions, so self-adjoint and symmetric, are not distinguished. They are both called Hermitian. So, but it's really important to distinguish them. So we will see in the third lecture why one should work with self-adjoint operators. A few remarks now. Now we know what is the adjoint of a densely defined operator. And in fact, we can give a characterization of a symmetric operator in the case where it is densely defined. So a densely defined operator T is symmetric if and only if its adjoint is an extension of T. So that's another way to express that the operator is symmetric. From the very definition of the adjoint, it's not difficult to see that the adjoint of a densely defined operator is also a closed operator. This is very easy. It's related with the continuity of the inner product. And if you combine these 2 points here, so we know that T star is an adjoint. If T is symmetric, densely defined, well, T star is just a closed extension of T. So it means that T is closable. Perhaps I can add a comment here in this case. So suppose that S and T are symmetric. So we have this. T is symmetric, so we have also this, and we had that S star is an extension of T star. So you see here, if you increase the domain of S in a sense to a symmetric operator T, well, the domain of the adjoint gets smaller. So one question is it possible to take the domain large enough so that T is still symmetric, so that these two guys are equal, namely that T is self-adjoint? And this is precisely what we will consider in the third lecture, the question of self-adjoint extension. A last point, you can see it as a kind of theorem, which says that a densely defined operator is closable if and only if the domain of the adjoint is dense. It's not very difficult to prove. Actually, one direction is very easy. For the other direction, you need to look at the graph and consider some operation I've not introduced on the graph, so you can just take it for granted. But I just want to add one remark here. So for a densely defined operator, we have defined the adjoint. We know what is the domain, but there's no guarantee that the domain is dense. Okay, at least when T is closable, you know that the domain of the adjoint is a dense set. I want to end the lecture with an example, the example of the momentum operator defined on the Hilbert space L2 of 0A. We will consider this operator on 3 domains. So in fact, we consider 3 different operators. So P1, P2, and P3. So the only difference between the domains are the boundary condition we impose at the endpoints of the interval. And the derivative which appears here is always the weak derivative. And a last remark on this, I mean, this condition makes sense, these conditions make sense because function having weak derivatives are continuous. So you're allowed to evaluate at a given point. Because if psi were only a L2 function, of course you can change a L2 function at any point without changing the element in L2, right? And but here this makes sense because psi is continuous. Well, it's obvious that we have these inclusion of sets, so therefore we have that P1 is an extension of P2 and P2 is an extension of P3. You can compute the adjoint of these 3 operators very much in the way we proceed in the last example. The only difference that is that you should take care of the boundary condition simply. For example, if you look for P1, so in its domain, there's no boundary condition, right? And in order for the formula of integration by part to work without boundary terms, you should impose these conditions so that there's no boundary terms. Yes, right. And similarly, so you get these adjoints. And then you conclude, for example, obviously for P2 is self-adjoint. P3 star is equal to P1, but P1 is an extension of P3. So you have this. So this means that P3 is symmetric. And for P1, well, P1 star is equal to P3, and P1 is an extension of P3. So the inclusion is in the wrong sense, so P1 is not a symmetric operator. Okay, so this ends the second lecture, and see you soon for the third lecture on self-adjoint extension, and have a good day. Bye-bye.